crank up the current a bit and get more of these ions coming out. They are pretty heavy, pretty powerful. So we can actually use them to smash out atoms of the lattice that we send them on. Let's say it's a metal, or in this case we have silicon oxide. And we can do this in a very controlled fashion. So we can actually pinpoint a location and say, here I want to mill a structure, and use the ion beam to remove here the surface material. In this case, someone made a Fresnel lens, and the total diameter of the lens is about 10 micrometer. So those are used for photonic experiments in small lasers, stuff like that. Also, the ion beam can basically mill through any material. We have some limitations. We are basically just shooting heavy particles down, and the material we mill away just flies off the surface. But unfortunately, if we dig very deep, it gets redeposited on the material, so we cannot mill arbitrarily steep canals or structures. There's another thing we can do with the FIB, and that makes it even more interesting than the milling. If we inject with a small needle, if we inject some gas into the chamber, in this, normally you use some sort of carbon compounds that bind to a metal or an insulator, you can deposit the material onto the surface. So this chemical bonds inside this carbon compounds get broken up by the ion beam, and you can locally deposit material. Here you see in the image some substrate. It's some chips on a silicon substrate, and here you see 5 small needles that come in, that actually, through which the gas that is used for this decomposition is pumped. With that also you can write very small structures. Here we see an example where you have, on the one side, you have the substrate milled away, and on the upper side there was some insulator deposited onto the substrate by this technique. And if you do it carefully, you can also even create 3-dimensional shapes. So now that we have the basics, what does this device look like? So here we have the newest model from Zeiss. It's pretty small. The electron beam column is here sitting vertical, and under a slight angle on the other side, you unfortunately cannot see it, is the ion column. Here is a close-up of the chamber of the microscope. Here in the middle you see the electron beam coming in. Here from this side, actually from behind, comes the ion beam, and you can mount your sample in a region where the ion beam and the electron beam cross. So that gives you the possibility to use the ion beam to change the surface of the sample while you are watching the whole thing with the electron microscope. Things wouldn't be complete without the hand. So I have this little video that maybe works. So typically you also in these systems have some sort of micro or nano manipulator. Here is some demonstration by Kleindiek. They built these grippers that can pick up nanometer-sized objects. You can transport them within the FIB. You can use the focused ion beam to cut off pieces of interest, take the gripper, move them around, weld them to other surfaces. So this is a pretty powerful tool. So now that we established what we have, what can we use it for? There are several applications. So these devices have become popular within the last, let's say, 5 years. Mainly in semiconductor industry, where they are used for failure analysis. They are most probably also heavily used for reverse engineering. I will show later and explain how that works and why these systems are so great for that. They can be used for rapid prototyping, especially because in a normal process it's very hard to, if you use lithography, it's very time consuming, so you would like to have a process that can quickly create nano-sized structures, and with the FRB you can even create 3D structures. The last thing I will talk about, which I think is the most relevant in this case here on this conference, is circuit modification. So, why is it so nice for failure analysis? So, what we see here is the chip-sided bond of a gold wire, and depending on, so there are many factors governing how this wire bonds, and this is a common cause of device failure, that one of these wires breaks or gets detached from the substrate. So the FIB allows you to basically cut this soft wire and cut through the very hard silicon without changing the surface. So you can here nicely see you get a very clean cut, you get the cut exactly where you want it to be. And you can later on have a very close look on this contact surface between the bond and the chip. Basically, that would be the first stage that allows you to image this whole thing in a scanning electron microscope. If you're interested in more detail, if you want to see structures or structure sizes that are much smaller than, let's say, 10 nanometer, you would possibly like to use a transmission electron microscope. This also has something to do with the first slide, with one of the first slides I showed, where you see that the electron beam, the signal that it generates does not come directly from the surface of the sample, but the electron beam goes into the sample several tens of nanometer, so you actually average over a very large area. So if you're interested in very small structures, you can either reduce the energy of the beam, that unfortunately reduces the resolution, or you can just cut very thin slices. And the focused ion beam does allow you exactly that. So you can, for example, if you have a substrate where you know there's a transistor in the middle, and you have pinpointed that this is the transistor that probably failed, you would like to see why did it fail, what happened. You can use this focused ion beam to cut out the small lamella. Then you would take this lamella with some manipulator, lift it out, put it either in the same device or put it in a different transmission electron microscope, and then you can really see here a slice through the transistor, and you can, if necessary, go down to atomic resolution. Another thing we see here, I will talk about also on the next slide. You can not only, in these microscopes, you can not only look at the image, you can also do, for example, some X-ray analysis, and that very nicely gives you very nice information about the material you're actually looking at. So this is some structure that was done at our university. That's some layers, very thin layers that were deposited in a chemical process. And the question was, how thick are the layers, can we see them, and what do they contain? So you prepare a lamella of the substrate in the same way I described. You put it into a transmission electron microscope or a scanning transmission electron microscope. One just looks through the whole substrate, the other one has also a scanning beam. The difference is not so big when it comes to resolution. Here you can see a picture that almost shows you atomic resolution. Unfortunately, it's a bit too bright in here, but maybe, I don't know. These little dots you see are not exactly the atoms, but this comes directly from the fringe or from the lattice pattern of the silicon. So, as I told in the first slide, when you send electrons into a material, you not only get other electrons out or electrons flying through it, these electrons get decelerated, and decelerated charges create electromagnetic waves. So what happens is you have X-rays coming out of the material. So if you scan your beam very finely over this surface, for example here, there was a line scan taken, so the beam was moved over the surface, and some energy dispersive X-ray analysis was done. You get these curves, and what these curves tells you is what material is there. So what it means is you can take any, say electronic, any transistor, a hard drive, take it, make a cut through it, put it in one of these devices, and within a day or so get exactly the composition, how it was built. Probably also, if you know a little bit, the methods that were used to making it. So that's why these devices are heavily sold for reverse engineering purposes. Another nice thing is, since you are able to make very thin slices, you can make the slices and after each slice take a picture and then run this series of pictures to the computer and get some tomography or some 3D reconstruction. So in this case that was done on a biological sample. For this, it used to be that the samples had to be prepared in a special way, frozen or embedded into some plastic. But actually nowadays even that is not necessary anymore. You can have a certain pressure in the microscope, so you can, not exactly living cells, but almost living cells, can cut them apart and look how it looks in the inside. So, coming to a more fun part, you can use these devices to create 3D structures. In fact, very small 3D structures. By taking a CAD file, people created, for example, this miniature toilet for this dwarfs, presumably, I don't know. You see the process is not perfect yet, so there's it's not straightforward to go from the CAD model to building one of these structures. But it's something that is worked on and probably will work a lot better in the coming years. This is also quite interesting. There they mounted a piece of graphite on a special holder that could be rotated. So they basically had a mini lathe, and they could mill away. So they had this thing rotating in this direction, and the beam came from the side, and then they could nicely carve out this miniature wine glass. So if you want a very small drink, that's probably the way to go. So now the important part, and unfortunately the one where I couldn't get pictures for. What I could get was this this advertisement I found on a web page that actually a company that offers this service to hardware manufacturers.